So what am I going to do to use the event we've generated here, this hit event? Well, I want to use it to create the particles which are going to create the explosion here on our sphere. So I'm going to lay down a source, and I'm going to call it source explosion. And I'm going to select the target object as the thing that we're going to emit particles from, and I'm going to emit them from surfaces random. And I'm going to have constant activation, and I'm going to give it a high value, but I'm going to make it depend on the event. So I'm going to use an expression, and I'm going to use the expression function pop event. And this takes the name of the event, in our case it's hit event, and this will evaluate 1 when the hit event has occurred and will otherwise be 0. So these particles will either be birthed or not depending on the hit event. And our impulse is set to 0. Well, let's try and see what that looks like. I'm going to have to combine these two sets of particles, and I can do that using a collect pop. That's the equivalent really of a merge SOP, and we just connect our two streams of particles to this to get a single collection of particles. And let's play and see what happens. And we can see that as our particles hit the sphere, they create new particles, and new particles are being created on that sphere, and the surface is filling up with particles, but they're not going anywhere. What I want them to do is radiate out away from the sphere. And one way to do that is to change the attributes of the sphere itself. And here's the sphere. It's just a simple polygonal mesh. But what I want to do is add a point SOB and use that to add normal information to the points. And we can see that that's worked. We can see the normals there. And now going back into our pop network and to our source node, what I'm going to do is take advantage of a peculiarity of the source node, which is if it finds a normal attribute on the geometry that it's emitting from, in this case our sphere, it will interpret that as a velocity and allow you here in the Attributes tab to use inherited velocity. And use inherited velocity will take that normal direction and give each of the particles a velocity depending on the normal. And you can also multiply it up, and I'm going to do that here. I'm going to give it a velocity of 10 times the normal direction, and let's see what that does. And we can see that that's creating these particles emitting from the surface. Well, I want to tweak that effect a little bit more, and in order to do so I'm going to need to create a group of the particles that have just been born as a result of this source pop, as well as a group of all of the particles that are in the explosion part of our simulation here. And I can do that by creating a birth group which I'm going to call explode initial, and I'm not going to tick preserve group, so that's just going to contain the new particles. And then I'm going to create a group which I'm going to call explode all, and I'm going to name the group $OS, and I'm going to make the source group explode initial, and I'm going to preserve group. This means that as I add particles to this group, it's going to just expand. And I need to have a predefined rule which is going to include everything from this explode initial group in our explode all group. And so I can set this to 1, and that evaluates to true all the time, and I've enabled this, so that should ensure that our explode all group includes all of these particles. So let's just see whether that works, and we can see that we've got 2,083 points created by this, and there are 2,083 points in explode all, 0 points in explode initial at the moment. The reason I've done that is because I want to vary the velocity of these particles. I want to vary the velocity in the sense of sending them in random directions. I want to increase or decrease the velocity as they head in the direction that they're heading. So I'm going to lay down a velocity pop, and I'm going to set it to the vector method. And this gives me an expression here, which is the current velocity. And I need to return a vector here. I need to have an expression here that evaluates to a vector. I've got a vector there already. So what I can do is times it by 1 plus rand $id. Rand $id evaluates to between 0 and 1, depending on the ID of the current particle we're evaluating. So this can be anything from just the velocity that comes into this pop up to twice the velocity in the pop. So again, let's have a look and see what that does. And we can see we get a much more interesting explosion. But it's a bit violent, so I'm going to add a drag on this side in order to give us a little bit less violence. The other thing I'm going to do is change the lifespan of these particles, and I'm going to give them a lifespan of 0.5 seconds. Oops. 0.5 seconds. Well, we can see that's still a little bit too violent, and the reason for that is that I made a mistake here on the velocity node, which is that I want to apply this adjustment to velocity only once when the particles are first birthed. I don't want to apply it at every frame. So what I want to do is apply it only to the explode initial group. And we should find, let me turn the drag down a little bit, that produces a much nicer explosion, like so. It's perhaps worth using this opportunity to say a bit about how the pop network decides which particles are affected by which nodes. Well, we've seen here with the velocity pop that we can explicitly set the group of particles which is going to be affected by a particular node. But there's something else going on here, which is to do with the structure of the network, because as we can see, we've got particles being created by a source here, and then they flow through a number of nodes until they reach the collect node. And on this side we've got another source, the location pop, and the particles flow through these nodes to here. So the behavior of the network is such that the nodes here apply only to the particles which have been created in the node here and where they're flowing through. Similarly, the nodes here are only going to apply to the particles being created by this source here. Well, the next step is to create a trail for these particles that are heading towards the sphere. And I'm going to do that using a split pop. So if I insert a split pop here, we can see that what this does is create new particles from the position of existing particles. And by default, from particle position is what happens, and we want to keep it at that. First of all, let me set the source group. I'm going to set that to initial, which are the particles that are being emitted here from this location pop. I'm going to birth between 5 and 15 particles, and I'm going to create a group which I'm going to call trail. And I'm going to give these particles a fairly short lifespan of 0.25 of a second with a variance of 0.05. And I'm going to inherit just the color attribute CD That's going to come in useful when we render later. And I'm going to set an initial velocity, and I'm going to set it to 0, which means the particles are just going to stay put when they're emitted. Well, let's see what that looks like. Well, we can see we now have more particles, but if I middle-click on this node, I can see that allegedly we've got 1,000 particles generated by this split, and there certainly are 1,000 points here. So what's going on? Well, the answer is that this is quite a common problem with particle networks, which is to do with how often the network is evaluated. And in this case, at the moment, we're evaluating the network just once per frame. So what's happening is we're getting a lot of particles superimposed one on top of the other. And that's why it looks like we've got a very small number of particles, but if we middle click here, in fact we've got 1,000. So what can we do to address this? Well, if we go up to our PopNet node, we can see that one of the parameters here is oversampling. And this determines how many times per frame the network is cooked. And at the moment it's just once per frame, but if I increase it to 4 times per frame, and then replay our simulation, we can see that we're getting a lot more particles. So the next thing I want to do is add some noise to the particles we've just created. And I'm going to do that using a curl noise pop. And a curl noise pop can be used to either update a force applying to the particles, update the particles' velocity, or in this case we're going to update their position. And the other thing I'm going to do is make the noise change slightly over time. So I'm going to offset the noise by $t times 2. And what we should see, there we are, is that the trails now move in this nice, slightly random way.